Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list published on July 3rd, 2025, so about 4 days ago. This paper investigates physics emulation, which is using AI to create a fast digital stand-in for a complex physical system, like fluid dynamics. It shows that these emulators maintain surprising accuracy even when compressing the data by up to 1,000 times. The paper is titled Lost in Latent Space, an empirical study of latent diffusion models for physics emulation. And as we'll see, this approach is not only accurate, but also very efficient. The authors find that diffusion models, a type of generative AI, are especially effective in this compressed or latent space. Alright, so this first figure gives us a great visual of how the whole process works. On the far left, you have the initial high-resolution state of the physics simulation. An encoder then compresses this, squeezing it down into that much smaller, blocky image in the middle. This compressed representation is the latent space we talked about. The core of the process is the diffusion model, which repeatedly predicts the next few steps of the simulation entirely within this efficient latent space. This step-by-step prediction is called an autoregressive rollout. Finally, a decoder expands the result back to a high-resolution image, which you can see on the right. Okay, so let's zoom in on that middle step, the diffusion model itself. This diagram shows the core of the process. On the left, it takes the current compressed state, a noisy version of the future states it's trying to predict, and the simulation's physical parameters. These are fed into a transformer-based denoiser. A denoiser is a model trained to remove that noise, and in doing so, it learns to predict the next sequence of states. This technique of predicting multiple steps at once is called temporal bundling, and the result is a clean prediction for the next phase. Moving on to the results. These charts show how well that initial compression and reconstruction step works. We're looking at 3 different physics simulations here. The key metric is on the vertical axis, variance normalized root mean squared error, or VRMSE. It's a standardized way to measure error, so lower bars are better. As you can see, the more the data is compressed, that's the red bars, representing compression up to over 1,000 times, the higher the reconstruction error gets. This makes sense, but what's surprising is how the full system performs despite this. Building on that, this next figure gives us a really nice visual comparison. We're looking at 2 different simulations over time. The top row is the ground truth, which is the correct result from the original slow physics simulation. The rows below show the outputs from the autoencoder alone, the diffusion model, and a more standard neural solver. What's amazing is that even with compression of over 1,000 times, the diffusion model produces results that, while not perfect, look very similar and physically plausible compared to the ground truth, often performing better than the standard neural solver. So we've seen the quality. But what about the speed? This table really quantifies the benefit, showing the inference time, which is just the time it takes to predict one step of the simulation. The original simulator is very slow, taking around 10 seconds per step. But look at the latent space models. The latent diffusion model takes just 84 milliseconds. To put that in perspective, a full 100-step simulation takes only 3 seconds with this method, compared to about an hour for the original. This is a massive speedup. Alright, so it's much faster, but how does the accuracy hold up over a long simulation? These charts compare our diffusion model, that's the solid lines, against a standard neural solver. On the left, you can see the diffusion model consistently has lower overall error. The bottom left plot shows the spread skill ratio, which measures how well a model captures the system's uncertainty. A value near 1 is ideal, and our diffusion model gets very close. The plots on the right show the power spectrum, RMSE, which checks if the statistical details are correct. In all cases, the diffusion model is simply more accurate. So to wrap things up, the big takeaway is that using diffusion models in a compressed or latent space is a game changer for physics emulation. It's incredibly fast. And surprisingly, the accuracy holds up even when the data is compressed over 1,000 times. These latent space models consistently outperform other neural approaches, especially over long simulations, because they better capture the uncertainty and statistical details of the system. This really opens the door for using these powerful tools in scientific fields, where both speed and accuracy are critical. That's all for today. Thanks for tuning in.